In this video, I wanted to start a review of the statics portion of the mechanical PE exam, specifically the machine design and materials one. So for this video, I wanted to start with equilibrium. So if you have a static body, that means you have to meet the terms of equilibrium, which says that your sum of the forces in the x direction equals the sum of the forces in the y direction equals the sum of the forces in the z direction, and all those equal 0. Additionally, the sum of the moments about the x-axis, the sum of the moments about the y-axis, and the sum of the moments about the z-axis also equal 0. So I have an example problem that I wanted to go over to demonstrate this. So here we have a cantilever beam, and it has a point load of 100 pounds at 1 foot, and then it has a distributed load of 150 pounds per foot, starting 4 feet off the wall and 1.5 feet long. We have two questions. The first one is to find the reactions, and the second is find the maximum shear force and bending moments in the beam. So to find the reactions, we're going to use those equations that I just showed you. But we're going to start by drawing a free body diagram. So I'm going to just transfer over the loads. So we have 100 pounds here, and we have 150 pounds per foot here. I'm going to go ahead and convert this into a point load, though, to make this calculation a little bit easier. We have 150 pounds a foot, and we have that for 1.5 feet. So we just multiply the 150 pounds a foot by 1.5 feet, and we're going to get 225 pounds. If this was like a triangular distributed load, you would basically find the area of that triangle. Times the height, which is 150 pounds a foot. So you get basically half of this number, so 112.5 pounds. And then when you have converted it to a point load, it's going to act at the centroid of the shape. So for a uniform distributed load, that's just going to be in the middle, 225 pounds. If this was a triangular shape, it would be 1/3 of the way from the tall end, or 2/3 away from the short end. And there's a bunch of shapes that they could throw at you, a bunch of different distributions. So this 100 pound load is 1 foot in, and then we're going to do 3 feet plus half of this 1.5, so plus 0.75 to get 3.75, since we're now the centroid, and there's another 0.75 to the end of the beam. So in terms of reactions, the sum of all of our forces in all the directions have to equal 0. So we only have forces in the y direction. So our only reaction force is going to be in the y direction as well. And then for our moments, since we're fixed right here, these guys are generating a moment. Or there's going to be a reaction moment here, I should say. Now, if you remember, a positive moment is counterclockwise, and a negative moment is clockwise. So these two forces together are going to be rotating us clockwise, which is negative. And so our reaction moment is going to be positive. Call it m sub r. So we can basically just apply those equations from earlier. So the sum of the forces in the y direction has to equal 0. So what do we have? We have negative 100 pounds. We have negative 225 pounds. Then we have positive ry. So ry is going to be 325 pounds. and then our sum of the moments has to be 0, and this is going to be about the y-axis, because if you'll remember, in 3D space, you have x, and then y is the one that's coming out of the screen towards you, and z. So since we're looking into the screen, it's going to be about the y-axis. So to account for our 2 point loads, we're going to do the force times the distance, and these are negative, so negative 100 pounds times 1 foot, and then negative 225 pounds times 4.75 feet, and then plus our reaction moment. So our reaction moment is going to be 1,168.75 foot-pounds. So these are the 2 answers to A. Now for B, whenever it's asking you to find the maximum shear force and bending or bending moment in a beam, you should think shear moment diagram. So I'm just going to replicate our beam down here. For whenever you're making a shear moment diagram, you want to make sure you keep your distributed load as a distributed load. And we're going to go ahead and draw our reaction forces on here as well. So we got 325 pounds. I'm just going to get rid of these. Sorry for my handwriting. And then we've got 1,168.75. That's foot-pounds. I will go ahead and keep the units. Now, whenever I'm drawing shear moment diagram, I like to start the left side of the beam and just draw a vertical line. And then I'll draw a horizontal line for the shear graph, a horizontal line for the moment graph. So I'll label these V of x and M of x. Okay, so for the shear graph, every time we have a point load, we're going to have a step change, and then distributed loads, it's basically going to be the integral of the distributed load. The shear graph is going to be the integral of this. So since that's a flat line, integral is going to be a line with a slope. So to start off, we're going to go up 325. I'm going to go ahead and draw some dashed lines on here just so everything lines up across the board. So we start off at positive 325, then we hit a negative, so we're going to go down 100, so we're going to be at 225. And then we don't have anything in here, so we're going to be flat again. And then we hit this distributed load, so remember, we're going to be doing the integral of that. So it's going to be 150 pounds per foot times 1.5 feet. It should be pounds per foot. Is 225, which is what we want to see, because we're at 225 and we should be to 0 at the end of the beam. But since this is distributed, we're going to go down just like that. If this was like a triangular distributed load, then the integral of that would be a curve. So you're going to start smooth or a relatively small slope, and then you would get bigger towards the end. If this was the other way around, then you do the opposite. You'd have a sharp fall drop at the beginning, and then you level out. Okay, so for a moment diagram, we have a point moment. Now, one thing that is a little bit of a pitfall you might run into is, even though this is a positive point moment here on our moment diagram, we're actually going to make this be a negative. So we're going to be down here, at negative 1168.75. And then we're going to go along, and for each of these sections that I have marked off with these dashed lines, we're going to find the area. Because if you think about it, these units are in pounds. If we multiply it by the distance, we're going to get foot-pounds, which is what this is in. So for this first section, we're going to have 325 times 1, which is just 325 foot-pounds. So we're going to do negative 1168.75 plus 325, which is going to be negative 843.75. And the moment diagram is the integral of the shear diagram. So since we're flat here, we're going to go up at an angle. And then for this next section, we're going to do 225 times, and then this is 3 feet. So 225 times 3 is 675 foot-pounds. So negative 843.75 plus 675 is going to be negative 168.75. And again, this is flat, so we're doing integral of that, which is just going to be the sloped line. And now at the end, we're going to have 1/2 times 225 is 1.5, which is 168.75, which again, that's what we want to see because we should be at 0 at the end. And this is not flat, that's at an angle, so the integral of that is gonna rise rapidly. It's gonna be a curve, but then it's gonna taper off at the end. Alright, so to answer our question, which is find the maximum shear force and maximum bending moment in the beam, your maximum shear force is just the biggest number on this graph, which is 325 pounds. And then the maximum bending moment is just going to be, I guess, the smallest, but the largest magnitude from the bending moment graph, which is 1,168.75 foot-pounds.